We're ready to introduce you to the moderator of our first panel session for the morning, Quantum Computing Hardware, Dr. David Moehring. Dr. Moehring is the CEO of IonQ, a venture-backed company developing general-purpose trapped ion-based quantum information processors. Prior to IonQ, Dr. Moehring was a senior national intelligence officer at the Intelligence Advanced Research Projects activity, where his high-performance computing portfolio included a global academic and industrial effort demonstrating quantum computing algorithms. Let's welcome Dr. Moehring to introduce his panel on quantum computing hardware.
Thank you. Yeah, thank you for the introduction. Again, my name is David Moehring. I'm currently the CEO of IonQ. I'd like to start by thanking Fujitsu for putting this meeting together. As it said on Twitter, so it must be true, I'm excited to be here and looking forward to the rest of the day. So very briefly, my background is my entire career has been spent in the development of quantum computing technologies. My PhD was specifically for the development of quantum computing hardware. But the reason I was invited to moderate this panel on quantum hardware was due to the previously mentioned role that I had at IARPA as a federal government employee, a program manager in the US government and the intelligence community. So as part of that activity, I had a worldwide portfolio of quantum computing hardware and quantum computing research. It gave me insight and oversight into basically all of the different technology approaches and many of the teams, also those who are present here. So through that program and many, many other programs over the last 20 years, sponsored by the government and others, the experts in quantum computing have learned a great deal about what it takes to make quantum computing viable, both what does work, what doesn't work, what does scale, and what doesn't scale. And I think the speakers this morning kind of highlighted one of the points that I also want to drive home very firmly, is that quantum computers are not more powerful classical computers. They can accomplish problems that cannot be done. I mean, if you can build a quantum computer, they can, which obviously is a big task in and of itself. But when you can build one, you can accomplish problems, you can solve applications that you can't solve with today's classical computers, or even 20 more years of fantastic Moore's law and Dennard scaling growth. You will never be able to accomplish these tasks that you can do with a quantum computer. And it really just has to do with a fundamentally different way that the quantum computers are built, the hardware, the software, the way they're operated, the way that they're programmed, and you're going to and even the applications themselves. And you're going to hear a lot more about those latter topics during the other two panels. And we're really focusing here on the hardware. And at the highest level, if you look at the way hardware is built, and Daniel touched on this very briefly, there's kind of two different ways of building quantum hardware. One is to take something that is more familiar, like superconducting loops or loops of metal, and to basically, if you cryogenically freeze these down to near absolute zero, then you can cool out all of the non-quantum behavior. You can cool out all the classical behavior, and then you can start to exhibit quantum features. And with those quantum features, you can build up a larger machine. From the other direction, you can also build quantum devices by starting with something that's natively quantum, like a single atom or a single photon, and then build out a larger collection of those quantum devices by having increasingly complex classical control around those systems. So to my current position for the last year, I've been a CEO of IonQ, which is a venture capital funded company. We're based just outside of Washington, D.C. And we're building the full stack quantum computing hardware, all the way from the hardware to the software and middleware and the firmware, all the way up to the cloud interface. And we're using an ion trap technique. So Daniel mentioned a couple of papers earlier, one from kind of our collaborators in the community, and also he mentioned Chris Monroe specifically by name, who is one of the co-founders of IonQ. And he highlighted the 10 ion qubit adiabatic work that Chris does. I'll also point out that on the archive last month was a 53 ion qubit simulation toolkit. Whether we count that as quantum supremacy, we're not going to debate here. That's not the focus of this panel. But as some in the audience will know, that the trapped ion-based approach uses the same quantum principles as what is used in atomic clocks. It's very well-behaved individual atoms that we understand from basic principles, and we can start to utilize that technology to build out this larger quantum computing hardware. In fact, probably almost everyone in here used atomic physics to get to the meeting today, because it's atomic physics and atomic clocks is what's responsible for the functionality of GPS. And because atomic clocks live in every GPS satellite device. So these are systems that run at room temperature and are based on that individual atom technology. So while we're a relatively young company, only about a year old, the devices and the experiments that we've already shown through the universities and some of the prototypes that we've demonstrated are already comparing well to our competitors and competitive mates throughout the ecosystem of quantum computing, and demonstrating universal quantum gate-based algorithms. So I'm excited for IonQ in the years and the months and years to come as we unveil more and more capabilities online, on hardware. And but for the rest of the time, I would like to take any questions about IonQ offline. Please find me during the break. Now I'd like to focus attention on the three panel members who really represent three kind of fundamentally different approaches to the quantum computing hardware. The first will be Jerry Chow and the IBM team, which are focused on universal gate-based quantum computing development. So as Daniel, again, thanks Daniel, you did a lot of my hard work for me. As Daniel pointed out, that a lot of the popularity behind the gate-based approach really came to light in the mid-1990s by the discovery of Shor's algorithm and other algorithms that have mathematically known advantages and speedups, exponential and polynomial speedups to any known classical approach. The second approach, also mentioned by Daniel, is what Eric Ladizinsky and D-Wave is doing with quantum annealing. Quantum annealing is not a general purpose universal quantum computer, but it has applications, most likely it has applications to what can be mapped to quantumizing and other Kubo-type problems. And then the final speaker is Tamura-san from the Fujitsu team, who will talk about actually classical digital annealer approaches, but that are based from it's inspired really by quantum physics as opposed to using quantum physics in the computations itself. And with that, each of the speakers will spend about 5 minutes presenting. We're going to start with Jerry and the IBM, and after that, we'll break into the panel discussion.
Okay. So I'm Jerry Chow from IBM-Q, where our research lab is out in T.J. Watson Research Center in Yorktown Heights, New York. And really at IBM, we've had a very rich history with quantum information and quantum information processing in general. From really the advent of the concept of quantum information from Charlie Bennett to even co-hosting that foundational meeting with MIT, which Daniel Adar mentioned earlier, where Feynman talked about simulating quantum mechanics, simulating chemistry with quantum computers. But at IBM, what we're doing is we're focusing on really what we think is the true value of quantum computing, which is this holy grail approach of getting towards a universal fault-tolerant quantum computer. That's really where there are proven speedups of potentially exponential speedups with things like Shor's algorithm. There are the known algorithms like Grover's algorithm, and also how we might actually deal with chemistry problems there. But in order to get towards that holy grail machine, we do believe that there's going to be a lot of near-term value. And that's through what we call an approximate universal quantum computer. So before we can handle the large numbers of qubits that we need for quantum error correction and all the overheads associated with that, we're going to have scalable architectures where you have qubits, but they're still going to be error prone. And even in the face of these errors, we want to be able to make use of it to the best of our abilities to demonstrate something useful. And it's really building up that type of platform where we have some errors, but we can actually look at the depth of the circuits. And this is a form of quantum computing which we're calling short depth quantum computing, where you're basically trying to get as much done in the circuit and expand into to as large of the quantum Hilbert space that you can, so that you actually access that full richness of the quantum Hilbert space to hopefully find something in it to solve some types of problems that might be of interest to you. And that's where we're looking at applications, again, in chemistry and potentially in optimization. So that's where we really see as our roadmap of building towards these near-term architectures where we're still error-prone, but we want to find advantage, and then the long-term, having that infrastructure in place to scale up towards fault-tolerant universal quantum computers. And so the approach that we work on at IBM is using superconducting qubits. So we're using fixed-frequency transmon qubits. They definitely need to be cooled down to really low temperatures, so in dilution refrigeration systems, as Daniel showed earlier. But really, I think what's phenomenal about the progress that's been happening in the community is where we've been able to take quantum computing from being something that's purely an experiment and something that a physicist needs to do, to become something that anybody can really start to pick up and learn about what quantum computing is about and how to potentially contribute to this really exciting field. And I think that's a testament to all the people who are here today and why we all are so excited about this field. And so we at IBM, we really are excited about trying to grow this rich ecosystem around quantum computing and having more people become quantum ready. So from various industries to new students to new talent learning about quantum computing, we feel that this is the time to get quantum ready. And we started that endeavor last year with what we called the IBM Quantum Experience, where we put a processor, a simple processor, on the cloud. So in May of 2016, we put 5 qubits on the cloud, made it easily accessible through this graphical user interface where you can drag and drop boxes to build a quantum circuit. It's been a really, to me, it's been a really rewarding project. It's been really exciting for our entire team to see kind of the nucleation of different scientists, different researchers who are starting to use it, tap into various communities such as developer communities, industries that normally are not going to do physics-based experiments. It's being used in a number of colleges, universities as part of the quantum mechanics teaching courses. We've had, as the numbers in this slide show, we've had 58,000 users, 35 plus external papers that have been able to make use of our service. And now we've recently upgraded to both a 5-qubit and a 16-qubit device that are accessible online. Yeah, so that QR code actually lets you access our quantum experience, where we really have a rich set of resources there, including a community where our research staff is ready to answer any questions and talk about quantum, any kind of questions that people have, as well as tutorials for learning about taking you through from simple examples of superposition to quantum algorithms. But it all fits within this framework of short depth quantum computing, where with the same type of online processor that we put there, you can actually run this chemistry experiment and simulate simple molecules like the ground state energy of hydrogen and lithium hydride. And we recently had this paper that just came out that showed the functionality of this short depth model and how we can use it in the near term to approach problems such as fermionic structure with these 3 different molecules. And then besides this kind of graphical interface, one of the real true things that we see about building this community further is to make a software platform that is really accessible by anyone. And so we've been working on this project, which we call Quantum Information Software Kit, or QISKit. And we released this basically in earlier May or so this year. And it's an actively growing community where we're trying to develop new Python tools so that you can actually run quantum programs onto any quantum backend. And so we have it currently tied into our available 5-qubit, 16-qubit backends, as well as quantum simulators that we have available. But really, the idea of this is an open source project. We want people actively contributing to it. It's on GitHub, and we're really excited to kind of foster this new generation of software development tied into the rest of the stack, right? Because it's really, as everyone's been talking about, a full stack problem of having everything kind of married together. And so we're really excited to work on this. I'm really excited to be here and kind of hear all of your questions and your thoughts regarding quantum computing. Thank you.
Thank you. Whoops, there we go. Hi, I'm Ladizinsky from D-Wave. I'm going to tell you about our approach to quantum computing. And first, I'd like to say I very much appreciated the remarks at the beginning. We currently live in a civilization, as was pointed out, where we have very large-scale problems that are provably beyond all classical resources on Earth. And the question we asked ourselves when we started this company, how do you create intermediate utility sooner rather than later? So if you looked at, there's lots of beautiful theoretical models about, say, the universal gate model of quantum computing. But when we looked at that, unlike a lot of companies, so a lot of people got into the field, they were doing basic research in academic institutions, and they wanted to continue that, say, in quantum computing, because it's what somebody did in graduate school. At the very inception of the company, we said, let's do a technology agnostic survey of all the different physical platforms you might use to do quantum computing and all the different models. The conclusion we came to after looking at all of those models and their relative merits and downsides was that building that sort of dream machine that Shor envisioned was daunting and would probably take decades. So what we said we would do is, can we pick a model of quantum computing that addresses large-scale problems, in this case, optimization and sampling, and can you evolve them through successive generations where somewhere in the middle, before you get to, say, a universal processor, you can provide value to the world at scale? So we've been going through various generations, starting off with exploratory R&D systems. We now have these second-generation quantum computers. They're not toys. You can put difficult problems on them. For artificial, say, benchmarks, we're exceeding state-of-the-art and sometimes matching very powerful computing resources on problems that are relevant. And we do have a path to universality by adding new interactions to our existing fabric. We've built this in a scalable architecture where we've coupled a mature superconducting digital control system to our qubits. Let's see. Our system is based on something Feynman envisioned a long time ago. This was a system of interacting spins. He asked the question, what's the simplest physical system that you could instantiate with which you could simulate the rest of nature? And the idea was a system of interacting spins. So each one of those little dots represents a spin, like a little magnet that can point up or down. They can interact with each other. And the question you would ask is, for a given set of couplings between those spins and little fields on them, how do you arrange the spins to minimize the energy of that system? That turns out to be an incredibly hard problem, and you can map a huge variety of problems to that architecture. So finding the lowest energy state or finding many low energy states is equivalent to a lot of big optimization and sampling problems, machine learning, et cetera. So we've built a physical instantiation of that. You can see our little artificial spin there. It's a ring. You can run current one way or the other way or put it in a superposition where it's doing both of those things. You can see a real circuit where we squashed and stretched out those rings. You can see 4 vertical, 4 horizontal, where they meet, they interact. And you'll say, well, look, most of what's there is not those qubits. Most of it is all of the control infrastructure. So we built the most advanced superconducting digital process in the world to access those qubits, program them, evolve them quantum dynamically, and read out their states. And you'll see it looks rather like a neural net, which lends itself to learning. Whoops, I'm missing something. Anyway, the applications that we're looking at, we think one of the most interesting applications is something called sampling. So machine learning right now, for all of its lauded in the press, most of what's going on is what's called regression and or pattern recognition. The real dream of AI would be for machines to look at complex data sets and not only infer insights and see patterns, but actually build a guiding theory that generated that data. So there's a part of machine learning that's been ignored called generative machine learning. And one of the things that might enable that is something called these Boltzmann machines, or in our case, quantum Boltzmann machines. And being able to generate all of these low energy distributions of that spin network, you could roll into a machine learning application and maybe enable generative learning. So we're very excited about that. Of course, optimization, constraint satisfaction. We've also been doing some spin glass material simulations where we can instantiate 3D lattices and look at their evolutions. We've built fully integrated systems at scale, superconducting quantum computing systems. These are a lot of our partners. You probably recognize that guy. This is the Google NASA system. We now have a system with Los Alamos, another company. So we've got a lot of partners buying systems and getting access. That's our 2,000 qubit system. There are people doing both basic science as well as real application work, whether it's Volkswagen or Los Alamos, Oak Ridge. So a thriving ecosystem. This was some data generated by Google, where it shows you if you're harnessing these quantum dynamics in the right way, what kind of speedups you could get. To make it simple, imagine building a maze. If you have to try getting through the maze one at a time, it takes you a long time. If somehow you could use superposition and tunneling, you might do it very quickly. We got something like 100 million X speedup on a D-Wave processor. This basically shows the potential of this. But at the time, there was another algorithm that people could use to get around using certain limitations in our architecture. Those architectures, in terms of the connectivity of qubits, are being addressed on future generations and won't be threatened by those kind of classical algorithms. We've been on a Moore's Law-like trajectory at D-Wave. So we have a fantastic interdisciplinary team. We do the design, the fabrication, the test, the building of all the infrastructure. And so now we're at this 2,048 qubits. Our next processor will be quite a leap from all of these, both architecturally and in every other dimension of the properties of that processor. Thank you. Not much time. Yeah.
Okay. Good morning, ladies and gentlemen. My name is Tamura. Today I'm going to talk about the digital annealer, or DA, which is Fujitsu brand accelerator for combinatorial optimization problems. So what is DA? The DA is quantum-inspired hardware. Its implementation is classical or digital. And I will soon explain how the DA is quantum-inspired and why digital is good. The DA uses the Monte Carlo, Markov chain Monte Carlo method to minimize the energy or cost function in the binary quadratic form. It can handle 1024 bits, which is fully connectable through 16-bit weights. To correctly use the Monte Carlo method, any flip that occurs in a specific bit, let's say bit I, should connect to other bits within an acceptable delay. To achieve this, we must have let's say one-to-all and also all-to-one connection for each bit. For 1024 bits, it is not difficult because by using standard digital technology, it's easy, piece of cake. For say 1 million bits, it's still doable because by digital circuits, we can increase the fan out as much as we like by using tree structure, exponential horn, those standard fan out schemes. Let me now talk about speed. Classical devices, by that I mean CMOS logic devices, cannot use quantum superposition or quantum entanglement to achieve speed. What CMOS logic devices can use is the power of numbers or parallelism. The effects of ordinary parallel computing, however, obey the law of diminishing returns because there's a large amount of, let's say, interdependence between computational processes, and also there are lots of overheads, like communication overheads. Therefore, in the DA, we use different types of parallelism, which I may call stochastic superposition. The basic search process, is parallelized, which easily results in a 1,000-fold speed up. And on top of that, we can use different parallelisms in a hierarchical manner. This expandability is the real beauty of digital technology. So thanks to the use of parallel processing, along with the circuit architecture specialized for stochastic search, the DA is much faster than ordinary simulated annealing or SA. When we used the 32 city traveling salesman problem, TSP, as a benchmark, the DA was about 20,000 times faster than an in-house SA code running on a 3.5 gigahertz Intel Xeon processor. Oh, and one more thing is the DA is not tailored to a specific program topology. I mean, DA is not making use of the topology information of a specific program type. The DA is much faster than SA, even for different program topologies other than TSP. The current DA supports a total of 1,024 bits fully connectable through 16-bit weights. This enables a straightforward mapping of practical combinatorial optimization problems onto the DA. We are showcasing some of the applications at the demo area. The applications we are currently showing are molecular similarity, which is for drug discovery, and financial application for portfolio management. If you are interested, please take a look at the demonstration at the demo booth and ask anything. Thank you very much.
Yeah.
Okay, so for the open panel discussion, I had warned them some of the questions that I was going to ask, but the first one is going to be seat of our pants. It's going to be addressed to Jerry, but it was largely derived from a comment that Eric made about intermediate utility. And so Eric touched on it briefly during his presentation, but what do you think, Jerry, is the biggest hurdle for increasing the pace of intermediate utility in quantum computing?
Yeah, I mean, so intermediate utility, at least with the types of systems that we're building, with regards to short depth circuits, all always, of course, improving the quality of the hardware, reducing the amount of decoherence. But even then, what we're already finding is that there are instances when as you build the processors larger, that you have crosstalk and issues like that, where there are actual errors that you want to be able to remove. And of course, we know that error correction is the thing that we all want and have more rapid development of. But even in the near term, in this short depth model, there's ideas and concepts for error mitigation, which the community is starting to actively work on. That I think will go a long way to making the near term available hardware much more useful towards actual problems.
Okay, thank you. Yeah, I assume that's going to be part of the second panel discussion as well today. So look forward to hearing their answers to that. The next question I wanted is to Eric, especially, I mean, kind of on this thread. D-Wave has been the earliest customer-facing kind of quantum entity. While there have been a lot of efforts at companies, D-Wave really has led the community in terms of talking with customers. And I'm curious what kind of changes you've seen over the last 10 years, and especially just over the last few years with other companies entering the community.
Yeah, so over the last 10 years, I think, well, so one, we picked, at the time we picked the adiabatic approach. Usually there's a prevailing paradigm, and the prevailing paradigm was, full universal gate model that. So one big change that I've seen is, say there's a program at the US government and Google's exploring it, this idea of building systems that are at their core more robust against decoherence and errors. So the whole reason the adiabatic model was interesting was that it's a lot less sensitive to noise. So we can get good results. The reason we can have 2,000 qubits with the kind of errors and noise that we have now, and that they work and actually get solutions to real problems, is that the model is fundamentally more robust. And so I think that this has kind of captured the imagination of a broader community, that this is actually an interesting approach, that has general applicability in the world in optimization, and now we have, the other thing is getting it in the hands of users. So whether it was the USC guys and Lockheed and then Google, getting systems in the hands of people and having them play with them has been really informative, because there's a lot of brilliant people out there learning things about how we embed our problems on a chip, requests, say, for more connectivity, more access to faster measurements, whatever it is, precision. We're starting to get informed by a broader community about how to design our next level processors. And so there's going to be, so I've seen excitement around it. People are starting to understand that it's real. I think we've changed the world's perception about the time scales when there will be quantum computers that have some utility, sooner rather than later, not 20 years or 50 years, but maybe in a few. So those are the primary ones, that people are open to new models, that there's a growing ecosystem of people who want to use and start understanding the future, and that we'll get there sooner rather than later as a general feeling in the community.
So just a quick follow on, in the prep room you mentioned the new connectivity of future devices.
Yeah, so one of the things that became very obvious, say with a lot of the stuff that we did at Google, they ran millions and millions of problems on our devices, and one of the requests, and we knew this, but it was emphasized that much more for us, is we really need more native connectivity. Each qubit right now has like 6 neighbors, and you can have more than that by what we call embedding. I can use intermediate qubits to create a connective tissue, but then you lose the total number of variables in your problem. So we have a very ambitious effort now going forward where the next processor will be a big leap from what we've designed up till now, and we're addressing all of the things that we've learned over the years. Higher degrees of connectivity and coherence, access to faster dynamics, all of that stuff, a lot of which we get a lot of experience by users using it day in and day out, running problems and looking at what mattered the most. So what pushes the needle forward the quickest? And sometimes there's a long list of things, but there's a subset of those that are the most important to getting to intermediate utility. You can't do everything. So that's another important lesson. Pick the things, the tall poles, get them into new processors, and go fast.
Thanks. Tamura-san, kind of a two-part question. given that you're working in non-quantum computing space, but you're still making like incredible advances in the classical approach. What do you think is the ultimate limitation of the approach that you're doing? How many more times can you improve it? How many more orders of magnitude? And what will it take you to switch over to kind of fully quantum?
Okay, I think the first question is in the kind of limitation of our approach in terms of speed and let's say the number of bits. You know, I would like to say one thing. Please understand that I'm not allowed to disclose the details of the hardware too much, but however, let me explain as much as I can. We have, of course, planned to increase the number of the bits that the DA can handle. And although I cannot disclose the future plan in detail, but the architecture of the DA enables us to achieve, let's say, 4 kilobits, 16 kilobits, and eventually something like 1 megabit and beyond. It is, matter of whether there's a market. So, and at the same time of increasing the number of the bits, we will enhance the speed of the DA so that we can solve larger problems within an acceptable delay. And that's the answer for the first question. And the next one is, do I have some plan to switch over to, real?
Or even what might be holding you back today?
Okay. It depends on the performance gain we can achieve by switching over to quantum stuff, because we know how much we can do with the digital implementation. And there is a compelling, reason that we have some significant, use performance gain by doing that. I mean, by moving to quantum, then we will not hesitate to adapt to use quantum, real quantum hardware. So it's really depends on whether real quantum hardware will provide compelling, performance benefit for our customer. Then we will move,
Okay.
But at this moment, we have our own solutions, and it will be effective for, let's say, foreseeable future.
Okay.
That's
Very fair. Very fair. So next question to Jerry. I'll do another two-part question. So the IBM Quantum Experience is really one of the first ones out there that was like fully open on the cloud. So what were kind of the unique, both from the hardware and just from the entire system perspective of getting that online? And then as a second part, what is the most surprising thing you've seen come out of that from the users?
Yeah, sure. I'd say that to get it to work was really one of these things where we had to evaluate the stability of the hardware, understand how long can we keep systems up, and how do we build in automatic recalibrations, things that basically keep the processor up online on its own for extended amounts of time, right? And a lot of work went into really marrying the experimental team with a more hardcore developer software team, and making things more user-friendly, making things that basically are superconducting qubit agnostic, right? It doesn't matter there's a superconducting qubit system underneath it, but defining all these interfaces to make it a usable entity. And so that's really, I'd say, those are some of the really exciting things about our team being able to work on these various aspects and bring it all together to put them online. In terms of what's really been what's been used on the system, I think it's been surprising to just see the amount of academic research that is enabled, for one, in terms of the sheer number of results that we've seen. But probably one of the more interesting ones was actually involved with some of your co-founders group. Chris Monroe's team looked at basically comparing how an algorithm runs on a trapped ion processor versus on our system. And I think that what that shows is that there's starting to be the need, as we have more and more companies or groups working on quantum processors, to have some type of defined benchmarks, defined metrics that go across the entire industry to tell us how good are these quantum processors. And there's been a lot of thought in terms of what is the one number, right? Because it's not just the number of qubits. 50 qubits isn't a magical number unless you have all the gate fidelities and all the coherence times and the connectivity that allow you to really do something interesting, or something that's beyond the capabilities of classical. So at IBM, we've actually been thinking about metrics like this. There's one we call the quantum volume. I talked to Joe Emerson here, actually, who has thought about other ones. And there's various metrics that I think that the community is going to be moving towards, that I think that is going to be really important.
Thanks. I'm going to take the second half of that question and also give it to Eric. What's kind of been the most surprising thing that users have mapped onto your problem, and what kind of results they've seen?
Oh, the most surprising things. Well, I think that, so for us, one was the amount of interest, and we've had two groups. We've seen people who want to do fundamental physics, like, hey, I want to explore spin glasses, or I want to understand quantum dynamics on a programmable system, and then people who just, like you just said, that are kind of, all they see is the fabric, right? So they see some dots and some lines, and I want to run applications. And so what we're seeing, I think, for me, what's surprising, it's an incredibly complex technology with lots of parts, and everything has to be just right. And so when we offered this, say, online, same thing. It's the full system. It's not just what the core quantum processor does. It's how well do you embed your problems? Is that a good algorithm? And so we've seen everybody from VW playing with it to do traffic routing optimization to facial recognition stuff that they were doing at Los Alamos. And I think what's fascinating to me is that how much of the performance depends on how you cast the problems and how you use the processor. So it's not just the core capability. We've seen, and this is very important when you put things online, right? So the user and how intelligently they use that, we have to make the system smarter and smarter, because you could have one user uses it in kind of an unsophisticated way and you don't get very good results, but it's not really telling you about the fundamental capabilities of the machine. Whereas another user will have a really good idea about how to use it and you get superior performance. So we've seen, I think we're at a point, for me, what's exciting is that it seems like we're at this tipping point where we've seen on even some real world-ish problems, parity with some very powerful computational systems that have taken 60 years of development and millions of man hours. We've seen parity and sometimes an advantage. And so I think we're close to a crossover point where we'll start in the next couple to 5 years be able to show real utility on these processors at scale. And we have a very aggressive program to address what we've learned about deficiencies in the core processor, but like I said, it's broader than that. You have to think about everything. And that user base, eventually you have to make it easy enough to use where you're not going to get disparity between users and results because of how knowledgeable they have to be about the processor. Yeah.
Okay, thanks. One more question for Eric that was kind of inspired by Daniel's talk earlier, where he really highlighted the importance of coherence and error correction.
Yeah.
So you've made a lot of improvements on your systems over the last 10 years, but very little has been done specifically on coherence.
Yeah, so I can address that. So it's not that we didn't care about that. It's just that in our model of computation, coherence means something very different. So in the gate model of quantum computing, one of they encode a 1 in a excited energy state, which has a tendency to want to drop to the lower energy state. which would be an error for them. In our model of computation, all of the computation is done in these low energy ground states, and we have an energy barrier that protects us from the little wiggles from the environment. So the first thing is that our system was much more robust to noise than, say, in the gate model. So that was part number one. The next thing is you had to build a physical system and see how it worked, right? And so when we first started building real systems, we have the qubits and all the control infrastructure and all the I/O and all that, and then we built things at scale. So most of the world was working on building really idealized qubits and making and what we realized is if I don't build those qubits in the context of a large-scale processor to begin with, a lot of that work will be irrelevant because those structures won't be relevant in the context of a real processor. So what we saw as we built stuff out, say for the coherence question, we were getting answers to problems at smaller scale with high fidelity, and we kept building bigger and bigger processes, and it was still working. We were still getting answers to, say, optimization problems. And we found that a lot of the issues were things like control error. So we had a whole list of, you have knobs that you turn to instantiate the problem. And if you have wiggles on the knobs, they might overwhelm anything you would see from, say, the coherence considerations. So we got to a point where we kept building more sophisticated hardware. We've seen evidence of some powerful computing, like I showed you that 100 million X result. And that's even with the processors we had with the kind of coherence times we have now. Now we've gotten to a point where to go to the next level, if we want to harness that, say, 100 million number, we found that one of the most important things was architectural, the connectivity between the qubits, which we're now working on aggressively. But we're also working on coherence now because we have an architecture, we believe that we can scale forward, we understand how to put all the pieces together, and now we're doing all kinds of new material science. But you have to be able to build it at scale. So it's not enough to do single demonstrations, but to build it at scale. So the answer is it worked up till now, I think because of the robustness against those effects, and now we're adding that as one of a long line of features that we have to improve to get value at scale, real utility.
Thanks. In the interest of staying on time, but also addressing any very pressing questions in the audience, I think we have time for one or two. Don't be shy. I see a hand in the back. Please speak loudly. Or with the microphone that's being handed to you.
Or both?
Or both.
So I just was curious about your thoughts on Intel's announcement regarding the 17-qubit processor they just announced yesterday.
Who was that question for?
The panel?
I can speak. I can speak to that.
Why don't you take it, Jerry?
Yeah. So I mean, it's exciting to see other industry players getting into the game of fabricating real hardware. We've worked on similar 17-qubit devices. It's part of our commercial program at IBM-Q. But also, in fact, the number 17. Why is it so special? Because it's the with regards to the surface code, which is one error-correcting code, it's an arrangement so that you can actually demonstrate a single logical qubit memory. And so you can see that there's a lot of groups working on near-term instantiations of quantum error-correcting codes and trying to demonstrate that you can fault-tolerantly protect a state. And so a system like 17 qubits allows you to do that in a distance 3 code.
Yep. I'll add that, I mean, the quantum computing community is relatively small. As Jerry knows from when I funded his work back in the day when I was in the government, I also funded that work. So those of us who know those teams saw it coming. And we look forward to seeing, as I think if you're talking about the YouTube announcement from the last couple of days, they said they're anxious to see how well this works, and so are we all. So we wish them the best of luck. Yeah. One more question right here in the front.
I have a question to Eric. Can you briefly describe how do you map the coefficient programming onto the real hardware? That means that often I see the Hamiltonian-based equation problems, but I don't know how, I don't understand how to map the coefficient to the real hardware.
Yeah, so that's very problem dependent. So we have a whole group that has to figure out how to take the hard part of a given problem and map it to this Ising Hamiltonian, right? So I'll give you an example, but I have to show you the equation. But say you're training a neural net, right? So when you're training a neural net, you set some weights on the neural net, and then if I'm trying to say recognize an image, I want to have a picture of you, I want to have it recognize that that's you. I'll put your image through maybe 10,000 images, and I'll get some error. And if you look at that error function between what you want the neural net to do and what it does, that error function will have a linear term and a quadratic term and something like the weights. So if you look at that error function, it looks a lot like that Hamiltonian. And so what you can do in that instance is say, okay, what I want to do in that neural net is find the set of weights such that I minimize the error over all of these instances. And so I can take that error function, I can stick it onto that Ising system, we can minimize it and then find those weights. So a lot of it really depends on the problem. So because it's such a generic function with this linear and this quadratic term, we do a lot of massaging where for any given problem, we'll look at it and then you try to find within the structure of that problem what's hard for classical computers. So one of the hardest things for neural nets is training them and finding that set of weights and minimizing that area over a lot of instances. In that particular one, if you look at that error function, you have something like a linear and a quadratic term. We can map that, minimize it.
Yeah, I'd like to ask you if the Hamiltonian equation is given, how do you map the equation onto the real hardware, your chip? On your chip.
Just an arbitrary equation?
Yeah.
Well, we don't put any arbitrary equation, but we do have, it is, and this would be, take quite a while to explain in detail, but you can show that it's classically universal. There's ways that we can instantiate, and or not nor like functions with where little blocks of optimization form gates, and so. But the answer is that for any given problem, one thing that you can imagine is, for a lot of people, you're running an algorithm. I have a function, a cost function of a number of binary variables, figure out how to arrange them to minimize that, and that's the hard part. There's a very, very broad class of functions like that we know how to map. And actually, and if people are really interested in a detailed way, you can go to our website, and there's tutorials where it'll show you everything from training neural nets to optimizing financial portfolios to modeling spin glasses. How to do that translation onto our chip and then run it.
Okay, thank you.
Sure.
Okay, so in the interest of time, I request that you take any other questions offline during the lunch breaks, and please join me in thanking the panelists.
Thanks. Thanks. Hey, nice to meet you.